Right, so this is the first meeting of the SAGE seminar for this academic quarter, and I'm going to talk about a project I've been working on. I'm not doing other things this summer, called Salvus, which is a name that suggests the relationship between this project and SAGE. It's just one of the Latin words that the word SAGE comes from, and it basically means safe in Latin. Right? My Latin knowing student.
It's been a while.
It's a Latin word at least.
Yes.
Okay. All right. So here are the goals of the project. One goal is to, and probably the sort of main technical goal is to make SAGE and other math software like R and maybe even commercial software very robustly available over the internet to a large number of users. So Salvus has not as its main goal. It's not about, say, packaging up SAGE to run natively on Windows or something like that. It's about making it so that if you are in any way connected to the internet, you will definitely robustly be able to use SAGE if you want to. Via cell phone, possibly, whatever, but the key thing you have there is an internet connection. Or if you have your own, as I'll mention a little later, I'm also interested in a situation where you have an internal network and you want to make SAGE available to a large number of users on an internal network. That's also important. Another goal is to generate substantial money that can support core SAGE development, because I haven't found any other way to generate substantial money besides doing something commercial. It can generate non-substantial money via NSF grants and donations, but they're typically a small drop in the bucket compared to the smallest even slightly commercial efforts such as Magma, and certainly vastly smaller than the revenue that's generated by Maple and Mathematica and so on. I went to a meeting at the Simons Foundation earlier this summer, which is a place that has a large amount of money, and it was billed as about finding a way to use their resources to support open source mathematical software, but it turned out to be extremely disappointing, so I don't think they really, I don't think that's the, unfortunately I don't think that's a solution to funding open source math software development. Also, if you look at how open source software development is typically funded in the real world, it's done mainly by companies. So Red Hat, for example, has done an absolutely incredible amount of really good open source software development, and they're one of the, they're in the Fortune 500 as one of the top 500 companies. They're in the S&P 500, for example. So they're a pretty big company, et cetera, et cetera. So I see this as a way, but notice that the actual development that I want to have happen is really the core mathematical development of SAGE. So development of core algorithms involving potentially very abstract research mathematics. The way I'm setting this up as a commercial venture is not by starting a separate company at present. I'm working with the Center for Commercialization on campus. They get 20% of revenue. The other 80% goes directly into the SAGE Foundation account, which is an account in the math department. And that money is pretty much unrestricted. I can use it for almost anything. Currently, it has some resources, but nothing compared to what this could potentially earn. If it turns out to be really successful, then at some point in the next couple of years, it could then be spun off as a separate company. But right now, I just plan to keep it within the university. It avoids a large amount of overhead, and it gives me access to a bunch of business and lawyerly type people, or actual lawyers. And really the main goal, the thing that I'm looking at in the long run, is to be able to hire a bunch of elite developers to work full-time on core research level mathematical algorithms. Maybe not full-time year-round, but full-time for certain amounts of time. So for example, I could, in theory, I could try to convince John to work full-time on algebraic topology code in SAGE 1 quarter instead of teaching. Could happen. Just an example. So the money could be used for substantial teaching buyouts and so on. When I arrived at UW, there were people here that thought that I had resources to do this sort of thing, and they would, faculty here, they'd pop into my office and say, please hire me to work full-time all summer on implementing blah, blah, blah in SAGE. And I would be like, I'd love to, but I have no money to do that. I could hire one of your undergrads for $3,000 all summer, and they would just look disappointed and go away. But if what I'm designing is actually successful, then I will have the resources to do that.
Retroactively.
No, not retroactively, but in the future. So there are many projects that are in various ways kind of overlap what my vision for Salvus is. Here are a couple of projects that involve a lot of programming and hosting of code in virtual machines, web interfaces that give you nice coding environments and so on. But I doubt if you search their entire websites, you'll find the word math anywhere. They have no special support at all for mathematical type stuff, which is actually pretty important and for what we're doing. I mean, there's a lot of subtle things that you want to do when coding in a mathematical context that I think don't get addressed very well by these systems. So one is called C9.io. It's basically something like the Code Mirror editor, except called the Cloud9 editor. It's just a competitor that I think maybe the Mozilla Foundation sponsor. But built around it, some people started a company where you can write code. You can edit your code online through your web browser and deploy it to run in a virtual machine. But I think there's much more to the problem than just that. Heroku is a popular cloud application platform. You write a bunch of code, and they have specific languages that will allow, like Python or Ruby, and you write a web application using those programming languages, and you can play them. But you couldn't possibly run Sage with this. Then AppSoma, that's another one that I learned about at the Simons Foundation meeting. I think some guy at University of Texas somehow wrote some web application and hooked it up with running on some instances on Amazon.com and charges you to use it. So at least it's been developed in a connection with education. I think the guy who wrote numerical recipes in C was using this in a course he was teaching, so his students would write their code on AppSoma. So there's certainly a lot of people thinking about how to program and make it easy to do through the web, but it's completely divorced from mathematics or the interests of mathematicians and math teachers and so on. Then there's, for example, Wolfram Alpha, which is all about doing stuff related to math, but it has nothing to do with programming or running code. So with AppSoma and Heroku and so on, at least these two, it's about potentially running an application that uses a lot of compute resources and runs for a very long time robustly and so on. So it's about being scalable and write programs. You can't write sophisticated programs and run big computations through Wolfram Alpha. You ask it kind of little questions. So it's a little piece of the puzzle. Then with Sage, there's the Sage Notebook, which I started writing with other people in 2006, and it lets you write code online and interact with the Sage session, and of course embed 2D and 3D graphics and so on, but it doesn't really enable sophisticated programming. It's really hard to edit files and work with a repository of code and so on. You don't have any capability to do that at all, really. And it also really isn't, it's just one thing running on one computer that isn't really that powerful. Then there's aleph.sagemath.org. Again, it provides features for working with things mathematically, but it's really just little snippets, so again, it's not really for serious coding or running something that maybe you want to have run for a month on 100 different computers or something like that. There's no feature, no support for that at all. Finally, there's the IPython notebook, which is pretty recent. And is actually quite a bit of code. It's thousands and thousands and thousands of lines of JavaScript and Python code. And it's primarily a local graphical user interface for using IPython that's built around a web browser. But it's not at all designed for multiple users at once, and it's really not set up for running on a remote machine. It works much better when it's just running on your own computer. So it's not really at all addressing the same problem. Then there's cloud hosting providers like Amazon.com. You can do anything you want with Amazon.com. You can rent an instance. You can start your own Sage Notebook server running on it. It doesn't have the same constraints as things like Heroku, where you can only run pure Python programs. Or actually, another one that I should have put here is Google App Engine, where you can run Python, Java, or Go programs. But again, there are lots of restrictions on how you can run them. Amazon, you can run anything, but the The main issue with Amazon is what do you actually run? So some people do try to do this occasionally. So you'd run, say, the Sage Notebook if you wanted to use Sage, but then there are a lot of issues with just running the Sage Notebook as it is right now that people run into. There's also Linode, which seems to disappear off the bottom here. It's another one. One of the biggest problems with Amazon is that there is a free virtual machine that you can get for trying out. It only has like 600 megabytes of memory and very little disk space, and you do have to pay for bandwidth after a certain point. So it's not enough to build. I tried to build Sage on it. I think maybe it finished after a week, but I couldn't figure out how to get the Sage Notebook to actually appear and so on. Maybe I just couldn't start up Sage. It was really, really frustrating. So at the free level, it's completely useless for Sage. You can pay them money, but it does start to get expensive pretty quickly. And it's a lot more than what you maybe pay if you, I don't know, there's a lot of services out there where you can get a free version or pay a little bit more, like Google with Gmail, you can pay more to have more space. Dropbox, you can pay a little more, etc. The amount you have to pay for these virtual machines is a lot more per month than you typically pay for any of these little extra services. So I'll give you some specific numbers in a second, where you can look. Okay, here's an example of a message. I think that, because when I changed the font. Okay. So here's an example of a message on the Sage mailing list a few days ago. Somebody named Chris Severinos kept complaining about his difficulty in trying to run the Sage Notebook. Apparently, he signed up for a company called Linode, which provides you a single virtual machine running on their servers. They charge you $39.95 a month for their cheapest machine. It has 1 gigabyte of memory, and he's trying to write the Sage Notebook for his whole class. And it's simply not working very well in 1 gigabyte of memory. Basically, 4 or 5 students start using it, and it comes to a complete halt. So he's writing back and saying how much memory do you need and so on. The people on the list, before he even mentioned he was using Linode, they're like, you need 8 gigabytes. You need more resources than you have. If you look at the Linode website, you can see how much they charge for, I don't know why exactly the prices are like this, but basically, when you look at cloud hosting providers, that is, places that let you rent by the month virtual machines, the prices are, they're like this plus or minus a little bit. They're kind of converging on a canonical price, presumably determined by the amount of money it costs to run a data center, the people that you have to employ, the air conditioning, the electricity, etc. And so here is your sort of 1 gigabyte of RAM, costs $40 a month. If you want 4 gigabytes of RAM and more cores, it's $160 a month. And this is pretty much what you'd want if you had any reasonable chance to run a Sage Notebook server for a small class of students. That's a lot of money, $160 a month, for an individual to spend on teaching a class. So my response to him is that costs a lot. The plan with Salvus is to basically buy a bunch of hardware using things like some extra money in the Sage Foundation budget, host it at UW, and then run code on it that makes it very efficient to use a whole bunch of different machines together to provide a resource, and I can charge a lot less than $160 a month. One of the reasons I can charge a lot less is because basically there's a lot of subsidies for hosting hardware at UW. The amount I have to pay for electricity is 0, the amount for network bandwidth is 0, and the amount for cooling is 0, and for the people that walk around and manage it is 0. So it's pretty cheap once you buy the hardware in the first place. Obviously, buying the hardware costs something, but even then, the amount you pay on buying a whole bunch of virtual machines over 1 year greatly exceeds the amount I've already spent on hardware. So it's pretty nice because I do this one-time investment, and then at the cost of me having to run around and do various administrative tasks, which I'm okay with doing, I can provide a service that I think will be cheaper. So stay tuned. Okay, so that kind of gives some background and motivation. Now I'm going to talk about what I dream of Salvus actually being able to do in 2 slides. Just a list of features. But you have to keep in mind with these features that, in a sense, you could perhaps whip something out in a hackish way that doesn't scale up, that could do kind of all of these things in a couple of weeks. But there's a big difference between doing that and writing something that scales up to potentially having 100,000 people at once using the system. So that sort of underlying architecture is what I'll talk about a lot in the rest of the talk. So first there'll be a simple starter page where you just go to the site, you type in some Sage code, you'll have tab completion, interacts, and so on, and you'll get your output. This is very much like aleph.sagemath.org, the single cell server, except that it will have a feature to browse. Basically, whenever you do a calculation, it will save it, and you can search through all calculations you've done so far. So you do some one-off calculation, instead of copying and pasting it somewhere else before you lose it, you could just delete it and do more stuff, but it'll still be there, and you can search through everything you've done so far. So it'll be storing in a database the inputs that you've given, which is different than what the current single cell server does. And it'll support mobile devices right off. So you can go to it right now actually, and that's what it looks like on a cell phone. So I'm using jQuery mobile so that you can use it through your cell phone, etc. The next thing that is very different than what the current Sage notebook supports, but is exactly like what Cloud9.io does, is that instead of having your kind of basic unit being a Sage worksheet or a single cell of code, the basic unit is going to be a Git repository, which you could think of as a directory of files with revision history. It could be linked to GitHub or some other repository or some other provider, but it will always be stored in addition on a local database that is in under my control. And so you'll make lots of projects. So if you're teaching a course or writing a book or writing a paper, you'll make one project just for that. And you can have a whole bunch of different files in there, like a whole bunch of different Sage worksheets, Python files, whatever. And there will be a command line where you can execute arbitrary Git commands. You can start up Sage and interact with this just like if you were logged into a remote Sage or a remote Linux machine with Git installed. In fact, there will be a remote Linux machine with Git installed. So you have the full power of this. Also, you'll be able to synchronize your repository back and forth with GitHub if you want to use the features of GitHub. So this will solve the folders problem and so on. It's just the classical collection of files in a directory structure. So things will be based around projects. And as I mentioned here, there'll be a command line. And if you want to see what this feels like, literally just try out c9.io. They give you a command line, they give you linking your projects with GitHub, and it just feels very natural. Also have some graphical way to browse your files. And what will happen is you'll browse through your files, and some of them, if they're Python files or Cython files, or say a CSV file with data, or a Sage worksheet file, you'll have different editors that can open the files, which will be implemented in JavaScript in the browser. So when you click on or ask to open an SWS file, then you'll get something that does look like the current Sage notebook, in the sense that it'll give you that worksheet with the input and output, and you interact with it in the same way. If you open a PY file, in contrast, you'll see a nice Python file editor, and you can edit it there, et cetera, et cetera.
When you open that SWS file,
yeah,
I can't then actually just use it as a Sage worksheet, can I? Like I can't. It's not.
Yeah, you won't.
So it's linked to a running.
There'll be a running Sage process
behind it.
Yeah.
Interesting.
Yeah. And you could have the option to either have several different Sage worksheets that are all pointed at the same running Sage process simultaneously, so that they have the same sort of state, or you could have separate Sage processes for each worksheet. So it'll just be like another tab, but that tab will look like the current Sage notebook, except it won't actually share any code with the current Sage notebook. You can publish, so publishing will be nothing like publishing a worksheet now. So when you publish a worksheet now, well, nothing happens because I had to disable publishing due to cross-site scripting attacks and so on the Sage notebook, but on your own local Sage notebook, if you publish something, it just would give you a link to that worksheet that you could see that was static. But instead, publishing will take the current state of your repository and some file that defines what should happen, and basically run a little web app that's determined by that file. So you'll get an address associated to that application, and it could be like a little interact, it could be a whole worksheet, it could be a whole book of worksheets, whatever. And your account will, so basically when anybody goes to the thing that you publish, then it will count against the credits in your account, just like with, say, Google App Engine or Heroku or whatever. So you'll be able to serve a certain amount for free, and then after a while you'll have to pay. Because if you set up a little application that, say, factors integers, every time somebody goes to it, then it's going to use a lot of compute resources as they factor integers. And so I can only give you so much, given that there'll be a lot of different users.
But they could also instead clone the Git repository and then make their own project that does the
Yeah.
same thing, and they would be paying instead of.
Yep. Although they'd have to set up Sage to run somewhere. So they might have to set up the whole thing to run on Amazon, and they will get so swamped in complexity, and they probably won't do it. And it will cost probably significantly more than I charge them. But for example, a person could decide to allocate 24/7 one CPU with a certain amount of memory to their site, and then pay $15 a month for that, and then it's done. And it'll be certainly less than what you pay for something at Linode or whatever. And then kind of the free pages will just get the extra stuff that hasn't been allocated, if there is any left. There'll also be some chat support. Okay. So just a kind of an overview of how I've been implementing Salvus. So basically, the entire approach is the exact opposite of everything I did with the Sage Notebook. There's kind of no overlap in what I do. So first thing is I'm taking my time and doing things right, whereas in Sage Notebook I didn't take my time. Essentially, the thing that I wrote in a sleep-deprived month looks like what we have right now, and it's really just been hacked to be more efficient by various rewrites of the underlying stuff. And really not a lot got done. But basically, the current Sage Notebook is not carefully done right. It's the opposite of that. It's another thing that's true about the notebook is it's one single monolithic application. You start up one program, it runs, it takes care of everything, it spawns other things, other Sage processes which it controls, but very monolithic, just like Sage itself, for that matter. In contrast, Salvus is service-based, and I'll show you a lot of this soon, but there are a whole bunch of independent components that have a clearly defined thing that they're supposed to do, and they run on many different computers. And if you find that you have an enormous number of people running Sage code, then you increase the number of Sage servers and the number of machines that they're running on, and then the web servers become aware of a much larger number of Sage servers and start balancing computations to a lot more of these things. But basically, you have a lot of independent programs that run by themselves and provide some sort of API. Like they listen on some port, or they serve something via HTTP, etc. So that's very, very different than what you have here. And in actual development, it feels extremely different because you have this command line program, say, with a list of command line options that you pass it, and you can sit down and work on it for a while and add another feature, and it's done completely independently of other stuff that you're doing. So you kind of really can switch gears and focus on very different, cleanly defined tasks without messing up other functionality. So whereas with the Sage Notebook, it's all kind of bound together in some terrifying mess. Another thing is that there's no single points of failure. That's a basic design decision in Salvus, which has a lot of implications, and I really only decided on recently. But so a single point of failure basically means if, well, you can define it in various ways, but if one thing blows up, physically, like somebody spills a cup of coffee on top of the computer, then your website continues working, possibly slightly slower, but it definitely continues working. So as an example, I don't know, maybe 2 weeks ago, all the power was off in the server room all day long because of the UPSs being swapped out. And I thought I would have no power outage at all. So all the Sage machines are down. However, if you were to go to https://salv.us, the Salvus website, the entire time it would have still worked. And the reason it worked was because the way I set it up, there's some Salvus server running on the machine in my office, there's some running on a cloud computing, or on some computers at a company called servedby.net, and there's a bunch of processes running down in the basement of Pedelford. And the redundancy is set up so that if any one complete site goes down, the other two continue to function and provide all of your data. So if users want to see what calculations they've done before, browse their files, it's all there, they can still do calculations. One thing they obviously don't have is that if there are a lot of people using the surface at once, it could be slower. So a single point of failure means that you can kill one single thing and the system continues to operate. The biggest situation when you make a web app where the single point of failure comes in, well, there's a couple, but the biggest central single point of failure usually is a database. You have a single relational database running somewhere. And typically what you'll do is you'll set up replication so that regularly that master database has its data being, every time you write to it, the writes are being sent to another database. But what you have to do is sit there and watch the master database and decide, did it go down? If something went wrong with it, then it went down. So then you have to make the slave database suddenly become the new master database. And you have to tell everybody that was using the master database to start using the slave database. So that I do not count as not having a single point of failure. I think that is a single point of failure. Unless you can really do that automatically in a way that works, which is really hard to do. And I'm not in the mood to do things that are really hard to do. So I'm not good enough to do that. So I'm trying to not do anything that's really hard to do. And one other thing is concise. So I spent a lot of time reading about other solutions to problems and trying to use them instead of just writing something from scratch because I knew how to program in Python really well. So I have many situations where I wrote an enormous amount of code and then just deleted it all and replaced it by a lot less code that used something else. I did that like 4 times over in many cases. So a lot of the code that is very important and central and it took me a lot of time to write is actually very short. The actual number of lines of code is, I think the biggest component I have is 700 lines of code. And when I want to understand how I automatically start up virtual machines, I can just read through the entire implementation in a very reasonable amount of time because it's 220 lines of code, which is good. So I really got obsessed with trying to write code that's short, not in the sense of just a few lines, but short in the sense that it doesn't take a long time to understand. This is the sort of thing you often simply don't have the option of doing in mathematical programming, like the sort of stuff we do in our research. I mean, algorithms just are complicated to implement. You're not going to, a lot of algorithms are just really, really long, and they involve a lot of steps. But often with this web design stuff, there are clever ways of utilizing well-tested, big, but very well-tested other components that people have used in good ways to make your life a lot easier. Okay, so here's the stack for Salvus. So starting at the bottom, I guess, or the top, there's the infrastructure, which consists of a whole bunch of computers, a whole bunch of a way to run virtual machines on those computers, and also virtual machines running on other people's computers in their data centers. And I'll talk about what the topology of all of this is right now. There is a virtual private network, so you have all these computers potentially all over the world, and you want to make it so that in writing your application code, it appears that they're all on one local network. So they all have very predictable static IP addresses that you can say, I'd like to have this machine come up with this IP address. Always. I'd also like it so that all communication in my local network is encrypted, even though really maybe the connection is going from my laptop over whatever network we have at campus, across the country to something in Virginia, over all kinds of public networks. I would like to not have to worry at all about encrypting, communication between the database and the program that's running on my laptop. So I'm thinking a lot about issues like this, given the name Salvus, where you're say working at Boeing and you type in some code that actually is confidential to your company, and you want to build a trust that that code isn't something that somebody else can easily see. With the current Sage notebook, it isn't very difficult if you work at it to see what other users are doing, because in fact, right now, all Sage processes run as the same user. So all you have to do is just start another process as that user that sort of watches to see what other users, which are the same Unix user, are doing. So I don't want that. And what that means is I have to worry about processes communicating in an encrypted way with, say, the databases and so on. So so to set up what's called a virtual private network, a VPN is where you have a whole bunch of computers that appear to your application to be on their own separate network where all connections are encrypted. And unless you're in that network, you can't read any of the traffic and you don't know what's going on. Uses public key cryptography extensively. So I'm using something called Tink. I'll say more about that in a minute. For the database, I settled on something called Apache Cassandra. I'll say something about which this could be, many of these tools, it turns out, could be really useful for supporting math research and stage development activities, but that won't be my main point today. But like, for example, setting up a VPN where every single build bot, every machine related to stage development is on that one VPN would mean that you could just join the VPN, and instead of having to worry about connecting to Skynet and then from Skynet connecting to another machine or connecting to some machine that's behind a firewall or in somebody's office, you'll just appear to have one single network everybody can connect to. So we should be setting up one of those for stage development. This database could be super useful for just storing data that comes up in mathematics research because it scales really well horizontally, as it's called. S-tunnel allows you to encrypt all communication between the user and the web application by just adding one program. So the user talks to that program, and then that program decrypts everything and then sends it on inside of the virtual private network. And so what happens is that instead of worrying about encryption within your whole internal infrastructure and in your applications, you just worry about encryption at one point in this one program called S-tunnel that runs completely separately from everything else. It's pretty nice. So, yes?
Not potentially a single point of failure?
Nope. It is potentially, but what you do is you actually run several of them, and in your DNS record you list each of them in the DNS server, so that when the client web browser says what is the IP address for https://salv.us, it'll get back several different IP addresses. It has its own decision-making process for which one it tries, but it'll try one of them, possibly at random or maybe based on some heuristics as defined by the web browser. If that one doesn't work, it'll go on to the next one. And so it's not a single point of failure. You run several different S-tunnels, perhaps one or two at each of the data centers. So for example, one of the S-tunnels was running downstairs when the power went out. There were 3 IP addresses in my DNS record for Salvus, and when a web browser, it tried to connect to the one downstairs, it got nothing, so it just gave up, and then tried to connect to the one in my office. That worked, and then it went on. So it's not a single point of failure. But as far as I know, the only way to deal with that is by putting multiple IP addresses in the DNS record, which is a little annoying because it's kind of like load balancing, but you don't have any control over the algorithm that the browser is using for deciding which S-tunnel to use. Nonetheless, if you type NSLOOKUP and give any famous domain, such as google.com, you'll see that they have multiple IP addresses in their DNS record. So I'm not the only one, or it's a common thing to do. Here, I'll just show you. So you might have thought that google.com was one IP address, or that the domain names map to an IP address. They don't. They map to n IP addresses, or potentially a very large value of n. So right now, at this moment, salv.us maps to those 2 IP addresses. Okay? I was torn about what to do, and you'll find people that strongly criticize this approach, but it works. So there you are. Any possible design decision related to writing a web application, you can find extensive arguments against it. I don't think there's anything that you can possibly find where there's some saying it's a terrible idea. Okay, so once the traffic gets decrypted by S-tunnel, S-tunnel has to send it somewhere, and it sends it to a program called HA proxy, which is a proxy server, and a load balancer. What it does is it takes the traffic and then it spreads it amongst many other web servers. Some of the traffic goes to a static web server, which I use Nginx for, and some of it goes to a more dynamic web server called Tornado. And I'll talk about those in a moment. So what it does is it looks to see whether or not these servers are up. If they aren't up, it doesn't send more traffic to them. If they are up, and it has like a heartbeat test to see if they're up, It does send traffic and it load balances, and you can control what algorithm it uses. For example, it might just round robin, or it might actually get some information about the current load and try to adjust based on that, or it might just randomly send users on. Or another algorithm is you look at some hash of the IP address that the user is coming from and use that to decide what web server the traffic gets sent to. Okay, so then Nginx, this is a web server, kind of competes with Apache and some of the other ones, but it has a fundamentally very different design than Apache. It was written by some Russian guy and has become maybe the second most popular web server in the world. Super, super popular because it's incredibly fast. The main thing it does differently than Apache is it has one single thread that handles an enormous number of simultaneous connections. So it basically does a little bit of work on each connection, going around in a circle. And it turns out that this sort of context switching done at the programming level can be done far more efficiently than actually switching between different threads for each connection. Thread switching is very expensive. There are ways to try to make thread switching quicker, like Sun had this T2 architecture that was supposed to do that. But at the programming level, I mean, he's just proved it with benchmarks. This thing is incredibly, incredibly fast. You just want to serve static HTTP content. So that's what I'm using. At some point, there are other ways to do static content where you put it on what are called these content delivery networks, CDNs, that are distributed. You pay somebody to host static content and distribute it around the world, and then when the user requests that static content, they get it directly from the CDN. But for now, this is what I'm doing. I also got a very large amount of free credits on Google App Engine, so I might be using that instead for all static content. Tornado is what serves the dynamic content. Tornado is a Python-based web server that I'll talk about, which is also very good and has some major distinctions from Flask. It's fundamentally very different than Flask. For doing mathematics, there's Sage, and I wrote a new program that basically starts a TCP server that a process can connect to. Then Sage forks off, handles that connection, and you have kind of this back and forth control of a Sage process that's running. It runs as a random. Basically, each time it forks off a new process, it creates a brand new Unix user that deals with all of that, with that calculation, and then destroys everything related to that user when it terminates. So it's a really nice thing, and what it does before forking, it preloads, for example, the plotting code, everything that's slow to import, it imports all of that. And so the startup time is very, very small. It's in the milliseconds, which is really, really nice. It's a little bit like what Volker wrote to get around the startup time issue with Sage. So this is, and I will very likely find a way to just include this component in Sage, because it would be nice to have anyways, included in Sage. For management, I'm using something called Paramico, which is an implementation of SSH from scratch in Python. So it completely avoids the existing SSH implementation. It's written in Python, but it's very, very powerful for controlling remote machines via SSH connections. It's really good. It's pretty amazing. It's one of those things that you could do. In fact, I wrote a bunch of code to do by using subprocess and SSH and stuff like that, but I ended up deleting that code because Paramico is much better. And it really fundamentally is providing you a surprisingly powerful tool, because instead of using SSH through subprocesses and that sort of thing, it literally just implemented the SSH protocol. And that provides all kinds of features that just would be very hard to do otherwise. It's much, much cleaner. It's really cool. Okay, so now a little more detail. So the way the web browser communicates with Salvus is using, well, there's this JavaScript library called sock.js. What this does is it uses something called Websockets when they're supported. Otherwise, it falls back to other approaches. The point here is that it allows you to have web browsers communicate with a web server in two directions very, very efficiently. So what happens with the current Sage notebook is a user connects to the Sage notebook via HTTP, and then if they want to do a calculation, like they do 2 plus 2, so they send the calculation they want to do as an entire HTTP transaction, So that can easily involve several thousand characters of overhead. There's all kinds of headers there. And then when they want to get the answer, they sit there and they poll. Every few milliseconds, they ask, hey, is there any output yet? And every single question, is there any output yet? That's several thousand characters going. An entirely new connection gets established. Several thousand characters are sent. Several thousand characters come back. With WebSockets, one single connection gets set up at the beginning, and then ever after you have this one single persistent connection. If you want to send 2 plus 2, you end up sending like 3 characters. Plus you may want to send like a null termination. I mean, you decide what you send. You send a couple of characters back and forth. There's no overhead of new connections each time. With the Sage Notebook approach where you have polling, it can work fine when you have maybe 100 clients. But what if you have 2,000 clients and they're all polling? Then somehow simultaneously, your web browser is going to have to handle 2,000 separate connection requests per second. Not your web browser, your web server will have to handle, say, 2,000 simultaneous connections per second. And that's just completely unreasonable for something like the current implementation of the Sage Notebook. Whereas if you have 2,000 WebSocket connections, that's no problem at all. So basically, using this approach, you can scale up a lot more than you can possibly scale with polling, which just involves sending an apps. I mean, literally just think about the amount of data that would go back and forth with polling with just a few thousand clients, and it becomes completely impossible. I plan to, but haven't implemented support for these other approaches. So I want to make it so that you can also connect to Salvus via a certain TCP port with SSL encryption. So if you're writing a desktop application or maybe a command line program that has nothing to do with a web browser, you'll still be able to connect and communicate back and forth, which I think will be nice. So you could have a command line program that feels just like you're using Sage, except that the commands are being executed by Salvus on a remote machine, back and forth. In fact, I have something like that already. I think I'm going to give a second talk where I demo many of these things, because it would take, if I tried to demo these things, I'd only get like that halfway through. So what I'll do is I'm giving you kind of the overview of everything that's there and why it's chosen, but I can give little demos of each of these things and how they fit together in a future talk. Like Bennett's could have lots of talks. Okay, so here's, just to summarize everything I said, here's an overview of what it looks like, of what Salvus looks like. So you have lots of clients. Typically, right now they're all web browsers, but they could also just be programs that would communicate via TCP. They talk to these S-tunnel processes, which then talk to HA proxy, which then balances loads and sends connections to Tornado servers. I didn't bother to put the Nginx servers in here, but I should. We just call that one Nginx. There are Sage server processes that talk to the Tornado processes back and forth, and the Tornado processes relay messages back to the clients. There's also Cassandra database processes running in various places. So it's a pretty standard architecture, really. It's a bunch of clients. There's something called SSL termination going on here. Then you have a load balancer, then you have a web server, then you have your back-end business logic, and you have your database. So it's every web application, every big distributed scalable web application has basically that architecture. It's just how you fill in the blanks that distinguishes them. By the way, there are a bunch of books on writing scalable web applications, like 3 or 4 at least. And I read most of them. They're all old. It's kind of weird. Like the guy one of the main people at Flickr wrote one, and some other people have written them. But they're all kind of dated. It's really annoying. Okay, so here's what the physical hardware looks like. Starting with, in the upper left, there's a little picture of 4 new machines that are each with 64 gigs of memory, 16 cores. They're 1U machines downstairs. Notice that I have a whole bunch of little 1-foot-long colored Cat6 Ethernet cables. I don't know, I think they're cute. Each one is a different color. Pretty cool. I'm excited because I got those yesterday. And they're really short and uncluttered. So I have these machines downstairs. It's a pretty significant amount of computing power right there. And I could have, for slightly less money, I could have bought one machine that basically has or for about the same amount of money, I could have bought one machine with 4 times as many cores and 4 times as much memory. But then if that one machine had a problem, the whole thing is dead. Whereas with 4 separate machines, I have more isolation, and if any one machine dies, I can just turn it off for a while or whatever. I have my other 3 machines. So for this application for Salvus, lots of little machines makes a lot more sense than one big machine, which is different than what you typically have with a lot of our math research type applications. Another thing is my office. I have a machine with 32 gigs of RAM, which this is like way less powerful than these other machines, but it's in my office, which means it's away from the terrifying and often failing power situation in the server room or networks. I mean, there's always something going wrong with the server room. So, whereas my office, the worst thing that happens is that it gets really hot in there and my machine crashes for that reason. But I stuck a fan and pointed it at my computer and it stopped crashing from the heat. Of course, then my fan broke yesterday, so we'll see how that. I have to get a new fan. I have a bunch of machines. I just purchased several machines and they're being shipped to the UW tower. So I don't know if you guys remember when there was the weird potential fire issue downstairs maybe 2 years ago in the server room, and there was this little frayed wire that was all burnt. And
So T2 had to be turned off.
yeah, T2 had to be turned off, etc., because of the massive power usage. The stats department had a huge cluster in there, and they just took all their equipment, at the time at least, and moved it to the UW tower, which is across campus. It's a co-location facility. I took a tour of that facility maybe 2 weeks ago, and it's a very, very impressive couple of server rooms. They have their own generator, they have their own geothermal cooling system. It's very cool. And I talked with them, and they'll let me host machines. But they call it hoteling, but they put me in the enterprise section in a rack. They charge about $20 a month per so per machine, which is pretty cheap given that similar hosting at a place like rackspace.com or something would be at least 10 times as much. So it's dramatically cheaper than what you can buy outside of the university. I think that's partly that things like tuition, federal grant money, overhead on my grants, etc., subsidize this server center.
But you buy the servers.
Yes, you buy the servers, you put them there, and they host them. And you have 24-hour access. You can get in there whenever you want. If the power of the world goes out, they still have power because they have their own generator. It's not really very useful because maybe you don't have a network, but it's nice to have such a hosting location. So I'm putting 3 machines devoted to Salvus in there. I'm also putting a 4th identical machine, which will just be for building Sage. It'll be a Sage build farm with a whole bunch of virtual machines running on it. So maybe 30 different virtual machines, a whole bunch of different versions of Linux and so on. And there's lots of disk space, so at least that one extra machine, well, I'll use some of the extra disk space for just backing up stuff over here. The network connection between the tower and here should be about the same as the connection between the machines here. It's solid gigabit Ethernet, so it should work well. So that's coming soon. They are supposed to arrive there on October 9th, which is next week, or a week from now. I have a couple of virtual servers. There's this, one of the students in my class, there's another student who started a cloud hosting company, and he's letting me use a couple of virtual machines on his cloud hosting service for free. So he isn't charging me $500 a month or anything at present. See how long that lasts. Google finally got into having virtual machines. They've had something called Google App Engine for, 4 or 5 years, but Google App Engine is very restricted. You can write a Python program, but you can't run, you can only run sort of very, very restricted stuff that uses their APIs. You can't compile C code or anything like that. But I was intrigued by Google App Engine, and I wanted to somehow write Salvus in a way that would build on Google App Engine. My original plan a couple of months ago is that everything except running Sage processes would happen on Google App Engine, and the Sage processes would run on Amazon's cloud. And right now, I've completely abandoned that because we had a Sage Days where we tried implementing something on Google App Engine and started realizing how expensive it can be. Basically, they charge you for every possible thing that you do, and it adds up. They have a free version, but every megabyte that goes out, every database access, they charge you for it, a very, very small amount. But when you start doing the math, if you don't write your application very cleverly, with lots and lots of caching and so on, it can end up being very expensive. So I was really worried about that, and I complained to Craig Sitcho, who was a postdoc here, and now works at Google about this, and he complained to somebody at Google, and then suddenly they magically announced, Google App Engine Research Awards for academia. And so I applied for one, and they gave me $60,000 in credits, which I can use. But by the time they actually gave it to me, I had written a very large amount of Salvus and had very much gotten away from the idea of putting everything on Google App Engine. Partly because I'm very worried about the single point of failure, and what I was after the 60,000 gets used up. You have to use it in 1 year. Once it's gone, okay, maybe I have to now pay 60,000 a year to continue running my thing that I'm only earning $30,000 a year doing. That would suck. So I'm doing the hard work now so that maybe I'll use Google App Engine somehow, but I'll have something more flexible. I also really didn't understand the economics of how much you can save by buying your own hardware and then leveraging the extreme extent to which the university is subsidizing hosting. I mean, whenever you get grants, there's this 55% or whatever overhead. That goes somewhere. It's really annoying, but it also means that we get really, really cheap hosting. And we have super fast bandwidth here. And every other cloud hosting provider, you spend hundreds of dollars just on bandwidth when people download stuff from your site. If I miss something at UW, there's no bandwidth charges at all. And our bandwidth is extremely good. Google just announced something called Google Compute Engine maybe 2 months ago, and it's actual virtual machines that Google hosts. So you can run absolutely anything in them, unlike Google App Engine. Unfortunately, due to technical issues, apparently I can't use my $60,000 towards Google Compute Engine. On the other hand, yesterday they gave me free 8 CPU instances with 100 gigabytes of disk space, as for some reason I had to fill out some forms, which made me feel very guilty because it was a survey where they had like multiple choice questions where none of them were valid answers. Like how much do you spend on hardware per year? $250,000 or more, $1 million or more, and those are the answers. So at the end, I felt really bad because I had to lie on like almost every question because there was no possible way to not lie. But anyways, they gave it to me, so I'll start trying to use this somehow. So this is even more resources that are available. So this is what I have to start with right now, and I estimate this should be easily enough to support maybe 1,500 users, paying users. So let's think about what the fixed monthly costs are. I'm hosting 3 machines at the UW Tower. That's $20 each for $60 a month. Okay, that's the entire fixed monthly costs because Served By charges nothing, Google isn't charging me anything, etc. So if I can make more than $60 a month, then I will be making a profit.
If Served By starts charging you, you can just
What?
put more. If Served By
Yeah.
starts charging you, just put more here.
Yep.
Well, but Served By has actually, you didn't give Served By machines, right? They were providing you server space.
Mm-hmm. Yeah, they just provision virtual machines on their own hardware, and that's it. And it's just started by some UW undergrad who knows another undergrad who worked with me on Sage. This guy Alex, and he just thought Sage was cool, so I would give him some virtual machines. And it's been nice because it's just like the whole campus goes boom. I still have some. Salvus is just still there. I can still use it on my cell phone even if all the machines in the math department are down. So now, yeah. So I met with a bunch of people from Amazon.com about. Amazon is the biggest cloud hosting provider by far. They're like huge in this domain. So I met with several of their people. They came by my office and we talked for quite a while. They said they would give me a bunch of free machine credits or something, but they never did, which is really weird. One of the main guys, like the head of open source evangelism at Amazon or something, his student took my class on Sage, a couple of my classes on Sage. He came to my class. He wrote a blog post about Sage, but then when I tried to talk to him about getting some free resources, he ignored all my emails. So, which is a little weird, but in any case, somehow Amazon is not providing me with anything, so I'm not really using any of their resources at present. And their free machines aren't useful, so we'll see how that goes. The cool thing about Amazon is they did, when the people visited, they explained some really subtle things that I might not have thought about, where there's kind of a whole stock market for Amazon resources, where you bid on, I'd like this many machines with this power, and you literally bid, and there's like a little auction, and there's a certain price, a spot instance price, and you can get access to a machine for a certain amount of time, much more cheaply than the published rate. But then, if you want it, say, for a full 24 hours, you might not be able to get it. So if you can somehow get in, use the machine for a while, and get out, that might be really useful for you. So they told me about that sort of thing because they figured that would be useful for academic researchers, which does make some sense. But it isn't really, because anyone with an NSF grant or anyone whose advisor has an NSF grant can automatically get essentially all the time they want in supercomputers by just filling out some forms online and being a little bit patient. So if you really just want to do like raw compute stuff for math research, then the best thing to do is just deal with the supercomputing centers instead of the cloud computing. And the supercomputer centers are a serious pain in the ass to use, but I suspect that, and I strongly suspect they'll start setting up virtual machines that you can just use at supercomputer centers. I saw something about this a few days ago, actually. In any case, the resources I have right now, which cost me $60 a month, should be enough to support several thousand customers. And if you think about how much money that could produce, it's kind of interesting. So here is just a little calculation. Let's suppose that people pay $10 a month, and you have 1,500 users. That's $15,000 a month. 20% of that goes to university. The other 80% goes to the Sage Foundation account. So that is $12,000 a month for just 1,500 paying customers. And that is substantially more than my salary. So that would be pretty cool to get to. That would make it possible to, well, it would make it possible to do a lot of things. It would certainly beat the $60 a month that I'm paying for hosting. And if you can get 1,500 paying users that really like the service, you can probably get 3,000. And you probably don't have to do much more work except add a few more machines to support 3,000. If you can get 3,000, I'd be able to get 6,000, which isn't really that many compared to the number of people that like using math software out there. And it starts adding up. Some other ways that this could make money. So $10 a month, that would be the sort of thing that would buy you some solid, dedicated sort of pro features, so more space for your projects, etc., than the sort of free version. But you could get higher levels of resources. So if you want to teach a class with 30 students, instead of spending $10 a month, maybe you spend $49 a month or something like that. And you get more resources, an amount that's pretty reasonable to have 30 people use the resources at once. So that could be a little stepping stone for people. So maybe they use Salvus where you're at $10 a month, they're pretty happy with it, they do something with a grant or with the university to spend some more money. Just like we spend a lot of money on things like WebSockets and so on. Similarly, money can be spent in this way. Site licenses where an entire university gets Salvus for all their students, and maybe it's $10,000 for the whole university or something like that.
That would still be running on your machines.
Yes. Or my machines in the sense of machines that I administer, which could very well be at Google or Amazon or whatever. On their machines. So suppose you're a company that is very, very paranoid about security. They exist. They could buy all the code for Salvus, a recommendation about what hardware to put it on. Maybe I would go there and help them install it, and they would pay a certain amount for the license to use the code, and they would then have Salvus, and they would get regular updates and so on. So you can imagine companies that might have that property where they're working on something, and they really don't want to, no matter what, no matter what sort of legalese I get C4C to say about how secure their data is, they can't possibly trust it on my servers.
So would those companies maybe also have like their own? Would they also be paying maybe to have their own version of Sage implemented?
Well, I think they would just get Sage for free because Sage is free.
Right,
but they would, but the thing to make it really easy for their users to use Sage.
Okay. I guess how would they develop their own version of Sage in this? Would they? I mean, you're not going to be going and changing the class structure, going into their files, but they just build it on top.
Well, that's a different question. Imagine that you have got to this level where you have 10 to 50,000 users, you have some site licenses. At that point, we can hire some full-time developers, and we can make developing Sage without having to modify the core Sage distribution itself a lot easier than it currently is. Lots of hand-holding, it could be done very easily, it's just not currently, because I think we have limited resources to spend on that sort of work. But I'm pretty sure there are people that if they could be paid, a real software engineer salary, would gladly do an extremely good job full-time working on making it really easy to do Sage development, or development on top of Sage for other applications. So that would be kind of one of the indirect goals of this.
Is this also why it's not open source?
Yes, if it were open source, it would be difficult to sell licenses, because you can only sell support each. Could be useful, but I've discovered already that like with the particular organizations I have in mind here, they don't go for that. Whereas they do they can justify much more easily actually buying software at a far higher level. So it's also not open source. So bits of it will get open source, but one of the other concerns is that first, if I work with C4C to make it so that they deal with all the billing stuff, they deal with they do a lot. But I know they'll do a lot regarding making connections. They know a lot of business people. They do like 10 startups a year or something. They require that the source code is owned by the university. So I have to work with them to open source things. They have concerns about open sourcing everything, especially from the very beginning, due to the fact that somebody else could just take all the code that spent a year developing, set up a very similar service, and charge less. So they didn't have to do that work. So as much as it pains me terribly to work on any code that isn't open source, I am biting the bullet and doing it for the greater good. Because what I really hope I can be doing soon is working full-time on things like, Hilbert modular forms, and sparse linear algebra, and all this other stuff that is so fun, making it super, super fast, but it's just, I don't quite have the financial resources to be certain that I can do that right now. But I think I will be if I get this going. Plus, this is actually really fun as well. Okay, so let's see. I'm not sure when I should stop exactly. I have the room until 2:30, but obviously I've been talking for an hour. This would be a natural stopping point, actually. The rest of the talk, which is basically half of what I've gone through, is a detailed discussion of each component and why. And it's very interesting, but I think I'll make it the next talk. Because every single one here, there's a whole bunch of stuff about how do you set up your own private cloud, why use VPN, why use Tink versus all the other choices, why use Apache Cassandra as opposed to PostgreSQL, all this stuff. And it's a perfect stopping point. So for this talk, I'll stop right now, and I'll talk next week about why to choose each of these components. And then the following week, I'll give demos and things and so on. Okay, thanks.